Right, so first section we're going to look at this week, kind of different than the rest of the sections, at least from tomorrow and Wednesday, because this one is more graphical. Tomorrow and Wednesday are not. Tomorrow and Wednesday are much more algebraic, where we're solving for like numbers. But today, not as much. Okay, maybe a little, but not as much. So we've graphed sine and cosine before. And we're going to use what we kind of know about those two to figure out what tangent would look like. Now, we mentioned this a couple times way back, so we'll see if we remember it. But you can write tangent as a fraction. Does anybody remember how you can write tangent as a fraction? It's this function divided by this function. Yeah.
Is it y over 1?
It's two functions. Two functions. Yeah. Okay, so if you want to think of it as a unit circle, it's y over x. But y is equal to which trig function? Y is the sine. And x is equal to which trig function? Cosine. So knowing that tangent is sine divided by cosine, that can help us figure out what this thing looks like. Here's your graph of sine. Looks like this, roughly. Here's your graph of cosine. It looks like this. They're both waves. It's just a difference on where the wave starts. With sine, it starts at the origin. With cosine, it starts at its highest value. All right. Now, first thing I want to figure out is when tangent would equal 0. What's the only way? So tangent is equal to this fraction, okay? What's the only way that a fraction can ever come out to 0? Yeah?
The bottom is 0. Top is 0.
The top is 0. Only way that a fraction comes out to 0 is if the top is 0. Look at the top. The top is sine. Now look at the graph of sine. Does the graph of sine ever hit 0? Eric?
Yeah.
Yeah. It hits 0 here. Brandon, what's this x value right here? 0. It hits 0 here. That's halfway through the cycle. Does anybody remember what that is? When you're halfway through the cycle of sine? Yep. Yep, pi. And it hits 0 again here. That's the end of the cycle. Anybody remember where the cycle ends? Yep. 2 pi. So it hits it at 0, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. Basically, tangent x is 0 whenever you have a multiple of pi, right? If you want to say it even less specific, tangent is 0 when sine is 0. Okay? So let's just keep those values in mind. 0, pi, 2 pi, and so on. Now, Zach said something else when I asked the question, how can a fraction equal 0? He said something about the bottom equaling 0. How about, Caleb, what function is in the bottom of that fraction? Cosine. And does cosine ever equal 0? Yeah. Here and here, at least in the first cycle. That's a quarter of the way through the first cycle right there. Does anybody remember what the point is when you're a quarter of the way through the cycle? Yeah.
Pi.
Yep, pi over 2. And how about 3/4 of the way through the cycle? Yeah. 3 pi over 2. Very good. All right. So what happens when the denominator is 0? That's a little different. You get a vertical asymptote. So anywhere that the denominator is 0, you're going to get a vertical asymptote. So pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. The pattern here, odd multiples of pi over 2. even multiples of pi over 2 wouldn't make sense. That's actually what I have right here. That's an even multiple of pi over 2, technically. You could think of it as 2 pi over 2, 4 pi over 2, 6 pi over 2, 8 pi over 2, so on. So, if you know where it's 0, and then you know where the vertical asymptotes are, then all we have to do on the calculator is test a value near the asymptote, and that'll give us our graph. Remember, when you test a value near an asymptote, what kind of number do you get? Like if the asymptote was at 2, and I plugged in 1.99999, I usually get one of 2 answers when I hit enter. Anyone remember what kind of answer we get? So think about like when we use the table on the calculator to do this. You've got an asymptote. It's something like 2. And I want you to plug in a number just before the asymptote, like 1.99999. You plug that in and hit enter. The answer in the table is either going to be this kind of number or this kind of number. One of 2 things. Yeah?
Really big or really small?
Yeah, really, really big, like 20,000, or really, really small, like negative 20,000. All right? So it either goes up very high or down very low. Okay. So let's graph tangent, see if we can figure out what it looks like. So I just copied the asymptotes over from the other page. Those were the odd multiples of pi over 2. Right? So we've got an asymptote there. We've got one there. We've got one there. We're going to have a bunch of them. Yeah, it's pretty close. All right, so there's my vertical asymptotes. Now, we also figured out where it hit 0. We said that the graph of tangent is 0 whenever the sign was 0. That happened at 0, pi, 2 pi, 3 pi. So let's graph those. 0, pi, 2 pi. Basically, what we're going to get here is a repeating pattern. I only have to sketch the pattern one time, and then you can copy and paste it and see what it looks like over and over. All right. Now, what I'm going to do is I'm going to sketch the pattern in between the first 2 green vertical lines. Okay? So what I'm going to do is check a value a little bigger than this asymptote and a little smaller than the second one. Okay? So pi divided by 2 is 1.57. Right? So what I'm going to do is I'm going to check a value just a little bit bigger than 1.57. In fact, you don't even need to know that it's 1.57. You could just take, don't do the tangent of pi over 2. You're going to get an error because that's a vertical asymptote. Let's just go a little bit bigger. So let's say tangent of pi over 2 plus 0.01. Just going to add a little bit to it. And I get negative, basically 100. So in other words, way down there. Now, let's check just before 3 pi over 2. I'm going to go just a little smaller. So let's bring up the same thing we just typed in. Okay, I'm going to insert a 3. And now, I don't want to do plus 0.01 because that would put me after the asymptote. I want to stay inside it just to show you what it looks like. So I'm going to go just before. If I check a value just before 3 pi over 2, I get 100. So I'm way up here. Okay, so what the graph of tangent is basically going to look like is this. It's going to stay near there. It's going to curve. And it's going to go like that. That's what tangent looks like. If I do zoom 7, you guys can see that. Did I type it in? You have to type it in if you want to see it. Okay, so tangent is basically these set of curves that just keep repeating over and over. I drew this one right here. That's what your graph of tangent looks like. Okay, so a little bit different than sine and cosine because you have to lift your pencil to draw it. That means this is not a continuous graph. Okay. So that's what tangent looks like. Now, think about cotangent for a second. What's the connection between tangent and cotangent? Yeah. They're flipped, right? They're flipped. That's the only difference. So cotangent is cosine over sine. So what that means is if cosine and sine switch places, everywhere that this graph had an asymptote in tangent, that's going to become a 0 in cotangent. Everywhere that this graph had a 0, that's going to become an asymptote. All the asymptotes and zeros switch places. That's what basically happens. And I think the direction of the curve changes as well. So remember, that's cotangent. I just wrote that, but I'm going to delete it so I can try to show you. I can't show you them side by side. But that's okay. We'll just look at them separate. Pi over 2 is where it crosses the axis for cotangent. Pi over 2 was an asymptote before. In the graph of tangent, pi is where it crosses the axis. In cotangent, pi is an asymptote. So all your asymptotes and zeros switch. Now, the last thing I didn't really mention that we kind of have to think about is this stuff in red here, in one period. I did the same thing here, in one period. Because what you have to kind of think about here, and I think the best way to explain it is to kind of think of like if you're in a movie theater. You have an armrest on each side of it. Right? Those are like asymptotes. You can't say that both armrests belong to you. You can't do it. Because if everybody said that, then it wouldn't work. Right? When you're sitting there, one armrest belongs to you. Maybe the one on the left. Unless you're sitting on the end, then that's different. But like say you're in one of the middle seats. Okay? Say the one on the left belongs to you. As long as we all agree that the one on the left belongs to you, then everybody will be fine. We all get one. Same thing here. You can't say, like if I put a box around this part, we can't say that both of those asymptotes belong to that green box. Because if they do, you're saying, okay, there's two asymptotes in that section. But how about the next section? Then there's only one now? They all have to have the same. So what we basically say is there's only one asymptote per section. Okay? The one on the left, the one on the right, that doesn't matter. Just as long as you understand there's only one asymptote per section. Okay? Not two. Because if you said there's two, then somebody would be left with none. Just like if you take both armrests, the person 2 over from you takes both, person in the middle has none. You all have to have the same. Okay? Same idea here. And same idea here. There's one asymptote per cycle in the graph of tangent. Okay. Look at this cycle for a second. It starts at 0. It ends at pi. So the length of that cycle is from 0 to pi. So from here to here, that's 3.14 units. That's different than sine and cosine. When we did sine and cosine, how long was it to get from here to here normally? 2 pi, 6.28 units. What that means is tangent and cotangent have a shorter cycle than sine and cosine, naturally. They have a shorter cycle. And that's what I'm going to say right here. So the period of tangent and cotangent is pi. without doing any transformations to it. It naturally just has a little bit faster cycle than sine and cosine. So remember what that means about the cycle. If the cycle is pi, that means you could take the tangent of 1 and you get that as an answer. If you take the tangent of 1 and you add pi, you get exactly the same answer. If you take the tangent of 1 and you add 3 pi, you get the same answer. You can add multiples of pi and it doesn't change the answer. All it does is put you in the exact same spot in a different cycle. Okay? You can add pi, you can subtract pi. Just like in sine and cosine, you can add 360, you could minus 360. Right? If I said to you, what's the sine of 370? It's the same as the sine of 10. Right? You're just in a different cycle, but the same relative spot. Bless you. So to kind of how you would say that formally is that if you take the tangent of something, it's the same as taking the tangent of that plus any multiple of pi. 1 pi. I mean, I showed you guys a few of them. Plus 1 pi, plus 2 pi, plus 3 pi. Same with cotangent. You have to take the like if you wanted me, let's say if this was in degrees, and you said, I want to know the cotangent of 800. And that's kind of big. That's hard for me to figure out. What can I do to make 800 smaller? Well, I can add or subtract multiples of pi. So I could subtract 180 as many times as I needed to make that number smaller and make it easier in my head to work with. Okay, so same idea as sine and cosine, except instead of 2 pi, it's just pi. Okay? And if you think, well, you didn't say add or subtract here. Yeah, this right here means add or subtract because n is an integer. If n is -1, then you basically have this, minus pi. If n is -2, it would be minus 2 pi. So if n is negative, that's how you get subtraction in there. All right, transformations. Okay, we keep bringing this up all year. Transformations are exactly the same. There is no change in any of the transformations that you're going to learn right now from what we've done before. Okay, so I've given you an example here, very generic, with tangent as the function. You could replace tangent with cotangent. A, B, C, D is the order we do the transformations in. And I just want to go through quick and have somebody remind me what each one of those is. So let's start with A. What kind of transformation is A? Yeah? Yep, that's your horizontal shift because it's adding inside parentheses. I'm going to jump to D just for the purpose of scrolling on the board. It's going to be easier for me to do it that way. What kind of transformation is D? Yep.
Vertical shift.
Yep, vertical shift. So D is your vertical shift. A is your horizontal shift. You can also call it a phase shift. Horizontal or phase means the same thing. What about B? Multiplication inside. Yep. Yep, horizontal stretch. We also call it a period change. Just a special name they use with trig, but if you guys call it a horizontal stretch, I'm perfectly fine with that. And what about C? Yep.
Vertical stretch.
Perfect. Vertical stretch. Right. So I'm going to write that as vertical stretch. What else? Oh yeah, B and C. What happens if B or C was a negative number? Yeah. Yep, it flips. That's a reflection. If B is negative, that's a horizontal reflection. And remember, horizontal reflections look like this. That's a horizontal. If C is negative, that's a vertical reflection. Vertical reflections look like this. Oh, actually, that's a bad example for vertical. Here's a good one for vertical. It's vertical. So, one question that I'll ask you about these is, you don't have to graph it. All we have to do is find the period. We had a formula for sine and cosine. T equals 2 pi over b. This one's very similar. This is t equals pi over b. Why pi instead of 2 pi? Because that's the normal period, pi. Where with sine and cosine, the normal period was 2 pi. Okay. Also, if you're not sure, well, what's b? Where do you get b from? It's the number in front of x. All right. So what I'm going to give you guys in a couple slides that's kind of helpful. Where is it? Is this table that summarizes asymptotes. Okay, so I'm going to give you this in a couple slides. The reason we're going to need that is because if you look at the original, right, here's where your asymptotes are. Okay, great. But I might ask you, what if you do a transformation? What are your new asymptotes? Okay, so you have to be able to find the new asymptotes if you stretch or compress or shift it. That's the goal. And that chart that I'm going to give you in a minute will help. Okay, so in general, to find asymptotes for any trig function, this isn't just these two that we're doing right now. This is in general for anything. First, you have to find all the asymptotes in one cycle of the original. And if you're wondering, well, how do I do that? That's where that table I'm going to give you is going to come in. Right? So you find all the asymptotes in one cycle of the original. In fact, that table will do that step for you. Okay. Next, set the asymptotes that you found in step 1 equal to the argument and solve. Okay, we'll go through and do one, but for now I just want to give you the steps. So if you had tangent, something like that, that's the argument. What's inside the parentheses. Stuff that's outside the parentheses does not affect your asymptotes. So only things that are going to affect your asymptote is the value for A and the value for B. Don't worry about C. Don't worry about D. Okay? C and D are vertical transformations. Think about a vertical line. It already goes up and down forever. If you take a vertical line and you shift it up 2 units, it still goes up and down forever. If you take a vertical line that goes up and down forever and make it half as tall, it still goes up and down forever. So C and D don't have any effect on this. That's why you set what is inside the argument, or set the argument, what's in the parentheses, equal to your original asymptote, and solve. Again, that table is going to tell you the original asymptote, so it's not something you got to memorize. And now, remember, anytime you have a trig function, there's a pattern to it. How often are the asymptotes going to keep repeating in general? Or how often does any specific feature in a trig function repeat itself? Every period. Exactly. Every cycle. You're going to get the same behavior every single cycle. So, how do you represent all the asymptotes? You can't just say this, x equals, and then just tell me a number. That's the asymptote. No, that's one asymptote. There's infinitely many. This is how you write them. tell me one asymptote that you figured out from step 2, and then tell me that it repeats every cycle. How do you say that? You put plus the period times n. So let's say you had an asymptote, just to keep it simple, at the number 1, and the period of your graph was pi. You would write 1 plus pi n. Okay, meaning you're going to get an asymptote at 1. Then you're going to get an asymptote plus pi units later. Then plus another pi units later. Plus another pi units. You're going to get an asymptote every cycle. Okay, so I might come back to these steps, but at least if you have these steps, that'll help us. Okay, so this one, I'm not too worried about asymptotes yet. All they ask you to do is find the period, and then show me a graph on the calculator screen that has 3 complete cycles. Okay. What's my formula to find the period of tangent? It started out t equals pi, yep, it's pi divided by b. B is the number in front of x. In this case, that's your period. So that number right there tells you how wide one cycle is. How many cycles do they want me to show on the calculator screen? Yep, 3. That's the width of one cycle. So what's going to have to be the width on my screen to show 3 cycles? Yep, 3 pi over 2. There's a lot of ways to get a width of 3 pi over 2. Okay? It's kind of like if I said to you, I want you to set a width of, I don't know, set a width of 5 on your screen. Well, you could go 1 to 6. You could go 12 to 17. That's a width of 5. Okay? As long as you set a width that you need, you can start and stop anywhere you want. Easiest way to do it, if you need a width that's 3 pi over 2, is go from 0 to 3 pi over 2. So that's enough screen space to show 3 cycles. Now we just have to type in our equation. And remember, I'm in radians. If you were in degrees, you would want to do, this is 90, right? 90 times 3 would be 270, 0 to 270. Right? But we're in radians. Okay, hit graph. Now, that's okay. You are going to get 3 cycles. You got a half, a whole, and then another half, which is technically 3. That's okay. Sometimes what we try to do is not break a cycle in half. So we adjust our window a little bit. So if you notice here, we cut off half a cycle. Right? The cycle of this is, what is it, pi over 2. So if we had slide our window a little bit, we could fix that. So we don't cut off that cycle. And we could have the edge of the screen right there. Okay? I'm not really worried about it. That's okay. It's not the best 3 cycles, but it works. Any questions on that? All right. So as far as how do you show the viewing rectangle, you just tell me the min and max. That's all. You don't have to worry too much about y min and max because it's going to go up and down. All right. So this one says, using the 2 graphs below, identify which is the graph of 2 tangent x and which one is 5 tangent x. So for here, you really just have to know what the 2 and the 5 are doing. 2 and the 5 are what kind of transformations? Jared?
Those are vertical stretches.
They are vertical stretches. Well, one of these graphs is stretched out vertically more than the other. Think about what would happen if you stretch something vertically. Like if you had a wire and it was all curved and you took the ends of it and you started to pull it, it would straighten out. So keeping that in mind, you should be able to tell which one of these is 2 tangent x and which one is 5. given that the windows are exactly the same. It's not like I zoomed in on one or the other. These are the same windows. Yep.
The first one was 5 tan.
Yep. That one's 5 tan x. And this one is 2 tan x. The 5 is stretched out more than the 2. So you'll have a problem similar to that on a test where, you know, I'll ask you to match something up. Now, I could throw a cotangent in there too. One thing about cotangent that gives it away is it curves the other way. Cotangent looks like this. Okay, so you can easily tell the difference between a tangent and a cotangent. Any questions on that? Okay. Now, let's take a look at secant and cosecant. Secant and cosecant can also be written with sine and cosine. One divided by cosine is secant. One divided by sine is cosecant. Brandon, if this one is secant and this one is cosecant, look at the denominator of the secant one. It's cosine. Does cosine ever equal 0? Yes. Cosine can equal 0. We just looked at that with tangent. And what happens if you divide by 0? Yeah. You get vertical asymptotes. Same thing with cosecant. Sine can equal 0. So you will get vertical asymptotes. So for this one, I'm not going to go through as much detail. I'm just going to kind of show you what ends up happening. But that is your graph of secant. Okay. You get these U shapes and N shapes. Now, cosecant, it's almost the same thing. But if you look carefully, I don't know, just pick a point and focus on it. Like secant, look at the U shape in the middle. The y-axis splits it in half. Look at the U shape over here. The y-axis doesn't split any U shapes in half. So one cycle, let me show you guys what one cycle would be considered. A full U shape and a full N shape. That is one cycle. So if I just kind of temporarily put a box on that, how many asymptotes do you have per cycle? If I draw it a little bit more accurately, let's go like this. We'll call that cycle 1, and this is cycle 2. Cycle 1 and cycle 2 each have to have the same number of asymptotes per box. If you have 1, you'd have leftovers. So it'd be like saying, okay, let's say that this asymptote right there belongs to cycle 1. Then what would that mean about that one? If we're saying that there's only 1 per cycle, then that one technically has no home.
So there's 2.
So there's 2. The 2 that I just put X's next to, those are in cycle 1. And if I just erase it so you can see it, you say, well, what about that one that I just erased so you could see it? No, that's in the next cycle. So secant and cosecant have 2 asymptotes per cycle. That's why I just listed some of the asymptotes. And if you're wondering, well, how did I get these? This is just where sine and cosine are 0. Same way we got them for tangent. We looked at the picture. But there are 2 asymptotes per cycle. Or per period. If I say period, if I say cycle, those terms mean the same. Now, here's your formula to find the period of secant or cosecant. It's 2 pi over b. In fact, this is the normal formula. Most of the time when you're dealing with a regular trig function, no transformations, the formula to find the period is 2 pi over b. The only time it's not is if you're doing tangent and cotangent. Okay, but that's normally what you use, 2 pi over b. And just like before, somebody remind me, what's b? If you're given a big thing, where do you look for b?
Number in front of X.
It's the number right in front of x. Yep. The a, the c, and the d they don't make a difference here. You're just focused on the b. And I'm not going to be having you sketch these graphs by hand either. Okay. I might ask you to do it on the calculator, definitely, but not by hand. All right. So what we're leading up to is a question like this. Find the domain, the range, period, and the vertical asymptotes. Okay. Domain, range, those usually aren't too bad. Sometimes people get a little period. Most people are pretty good with that because you just use the formula t equals. But it's the vertical asymptotes people get messed up with. So this is how you find vertical asymptotes. So I'm going to use some notation here, x sub 1, x sub 2. All that x sub 1 and x sub 2 mean are those are the asymptotes in one period. Okay. So I'm going to go back to the steps I just wrote. First thing you have to do to be able to tell me what the asymptotes are going to be in a function if you do a transformation is this. Step 1 and step 2. Solve for the new asymptotes. This, I scroll down a little bit. This x1 that I'm circling right there, the way you find that is to do step 2. What's circled in green is what I'm talking about right there. This number, pi over 2, is going to help you to do step 1. Pi over 2 is in the original column. Step 1 says find all asymptotes in the original function. Well, you're not even going to have to find them. All you're going to have to do is look them up in that table. So step 1 is going to be done for you if you copy down this table. Step 2, yes, you have to do that by hand. So, one asymptote that's in tangent in the original is pi over 2. New asymptotes, basically all this column on the right tells you is that there is one answer I'd be looking for. Cotangent. It has an asymptote in the original graph at 0. And I'd also be looking for one answer. Now, with secant and cosecant, there are 2 asymptotes in the original graph per cycle. So when you give me the answer for this one, I want you to tell me where did the first asymptote shift to and where did the second asymptote shift to. You need to tell me both. And same thing with cosecant. Cosecant has 2 asymptotes. These are the 2 originals. And you might say, why did I pick these 2? I mean, there's infinitely many. I could pick any that I wanted. My pattern here is to pick the first asymptotes around 0. I don't want to pick the negatives because it's just more work. But I try to pick the smallest positive ones that I can for the original asymptotes. You're not wrong if you pick something else. It just makes the arithmetic harder. All right, so a lot of information here. Really, it starts to make more sense when we try a problem. Okay, so we'll try a couple of these, and these are pretty much by hand. And then the last thing I'll have you guys do is just try graphing something on the calculator. All right. So this one says find the domain, range, period, and vertical asymptotes of secant. All right. Let's start with the range. I'll come back to domain. So secant. How do I type in secant? Because I don't have a secant button. Yep.
1 over sine?
That's cosecant.
Or 1 over cosine?
Yes. 1 over cosine. Now, I know I'm not looking at one cycle. I'm just interested in the range. So, question is, does this graph go up forever?
Yeah.
Yep, it does. Does it go down forever?
Yeah.
Does it hit everything in between?
No.
No. There's a gap. And if you're like, well, what do you mean, does it hit everything in between? When you're trying to figure out the range, pretend like you have a horizontal line. Drag it up and down. Yep, you're going to hit it and hit the graph. It hits the graph, hits the graph, hits the graph. Oh, wait a minute, misses the graph. So here's some values that are not in the range. Anything in this middle section. How do you think I could figure out how high the lower part of this graph goes? Like the highest. Yep.
Calculate the maximum.
Yep. Second calc, maximum. It's going to be the same on all of them. Doesn't matter which one you pick. Go to the right, or go to the left, go to the right, hit enter. The maximum of this lower section is -1. Now, you can probably tell just by looking at it, what do you think the minimum is of that upper section? 1. So this graph goes from -infinity up to and including -1. So it goes right up to -1. Or from, where does it pick up again after -1? 1. And Jacob, how high does it go? Yeah, it goes infinitely high. So there's your range. All right, let's do the period. We're dealing with secant. What's the formula for the period of secant? 2 pi over b or pi over b? No, pi over b is just for tangent and cotangent. Yeah, so this one's the 2 pi over b. 2 pi over, what's b in this case? 1. So it's really, the period is just 2 pi. In other words, it's the original. There's been no transformation. You could look at the original problem and see that. There's no change. All right, so we got range, we got period, asymptotes. Let's go back and look at the directions. Step 1, find all asymptotes in one cycle. Step 2, set those asymptotes equal to the argument and then solve for x. Okay, so we're dealing with, let's go back and look at our graph. Secant. Find all asymptotes in the original cycle. There they are. Pi over 2, 3 pi over 2. Pi over 2, 3 pi over 2. It says to set each one of those equal to the argument and then solve. What's the argument here? Oh, lies. What's my argument in f of x? not sure. Anyone help him out? What's the argument to the secant function right there? It's what's being plugged into secant. So, okay. Let me go back here for a second. So on slides somewhere, I explained what argument was. That's the argument. So you look there. Let's go back here. So what's the argument to secant? X. That's what you're taking the secant of. So set each asymptote equal to the argument and solve. Okay. Now, Brianna, if I want to solve this first one for X, what do I have to do? To get X by itself here? X already is by itself. The problem would have been if the argument was like a 2x. If you had something like this, then you got a little work to do. But in this case, there was no number with x, so that's it. You have found these two things. Okay? They're the same as the original. There's no transformations happening in this problem. So you've got x1 and you've got x2. So x1 is pi over 2. x2 is 3 pi over 2. Last step. Put plus period times n. This is why I had you guys find the period before we got to this step. Period is 2 pi. So plus 2 pi n plus 2 pi n. Those are your asymptotes. In other words, they're exactly the same as the original. There was no transformations that happened. And now, your domain. Well, what do you think the domain is? Like, how do you describe the domain in terms of the vertical asymptotes? The domain is what? Yeah? Looking for something kind of just in general. Yep.
Where x? No.
So let's start like this. The domain is all x values except. Yep. Yep.
Except when y equals 0. Or when y is an asymptote.
So the domain is all reals except these values. Because these are asymptotes. You're not allowed to plug those in. So the way we could say it is the domain is all reals except asymptotes. If you want to be more specific, you could say, well, here's what the asymptotes look like. These are your asymptotes. So plug in any number you want, except ones that would be in this black box. Can't use those. Okay. That's domain, range, period, asymptotes. Okay, I was going to do it for cosecant, but cosecant, there's no transformations. Let's jump to one where there is. So I'm skipping example 4, I'm going right to 5. Find the period and the asymptotes. Okay. Okay, what's my formula for the period of cosecant? Yeah, exactly. 2 pi over b, and in this case, b is 3. That's going to be important for doing the graphing calculator part to this problem. That's also going to be important for finding the asymptotes. Okay. The 2 pi over 3, that's going to be the plus period times n part. Okay. Step 1, find your original asymptotes. Can someone tell me what are my original asymptotes for cosecant? Okay, and I know a lot of you are flipping back looking at the table. That's good. I'll be honest with you, I don't even memorize that table. The way I do it is I think in my head, okay, cosecant is 1 divided by sine. Sine's in the bottom. When is the graph of sine? 0. So then I visualize this in my head. And I ask myself when that graph crosses the x-axis. And that's the answer to this problem. At least the first 2 spots. Okay?
Pi and 2 pi?
First 2 spots.
Oh, 0 and pi.
Yeah, there's technically nothing wrong with saying 2 pi. It's just if you go back and look at the table for cosecant, I gave you 0 and pi. Okay. Now, so we've got those. So off to the side, I'm just going to put those over here. I'm supposed to set each one of those equal to what?
dr.
Yeah. And Elias, what's my argument here? 3x. Take your first asymptote, set it equal to 3x. Take your second asymptote, set it equal to 3x. What we're basically doing right now is we're just figuring out where these 2 asymptotes shifted to, or stretched, or however they moved that we're finding. Okay. Jared, how would you get x by itself in the first one?
Divide by 3.
Divide by 3. Divide by 3. The first asymptote didn't move. Think about it. If you have a number at 0, and you do a horizontal compression, which is what this is, take 0 and compress it. Still 0. Doesn't go anywhere. Let's look at this one. Divide by 3. And you get x equals pi over 3. That's where your first 2 asymptotes are now. In general, Nakira, how often does an asymptote repeat? It's very general. How about in a trig function, any specific behavior that you notice will repeat itself every... Sure, Chris? I'm thinking of a word.
Period.
Every period. So this asymptote is going to reoccur every period. This second asymptote is going to reoccur every period. So tell me that. Say, okay, so the asymptotes are 0 plus every multiple of the period. 2 pi over 3n. And the second asymptote starts here, but it also will repeat every multiple of the period. So what, Sam, what would I put on the end of this one?
Or no.
So go ahead and tell me one more time.
Well, I said n, but
We got to have more than that. It's plus the period times n.
no. 2 pi, right?
N. Yep. So if you add 1 multiple of 2 pi over 3, you'll get the next asymptote. If you add 2 multiples of 2 pi over 3, that'll move you 2 cycles down. If you add 20 multiples of 2 pi over 3, it'll move you 20 cycles down. But these are your asymptotes. Okay, and they wanted me to show a window with 2 cycles. What's going to be the width of my window to show 2 cycles? Yep.
4 pi over 3.
Yep. So I think easiest way is just to go 0 to 4 pi over 3. So once we type this in, if we do it right, we should have 2 full U shapes and N shapes. 2 U's, 2 N's. Let's see, cosecant is 1 divided by sine 3x. Let's see how we did. So there's half a cycle. There's one full cycle. That's 1.5 cycles. And 2 full cycles. 2 U-shapes, 2 N-shapes. Perfect. And we didn't even cut a cycle off in the middle this time. It's even better. Any questions on that? All right. So, last thing is solving a trig equation on the calculator. You know, without even me showing you the steps, how do you think you could solve that?
Figure out where the x-intercepts are, or the zeros are. Oh wait, no.
Not intercepts. Anyone have another idea how we could solve that? Yeah. Okay, you could move everything to one side and then do what Jared just said. Find some roots. Or what if you want to leave it just like that? You could type it in just like that and then do what? Yeah. Yeah. You're just gonna see where those cross. That's all. Just remember though, if the graph looks like this, that's your graph of cosecant. Here's a graph at -1.6. How often will the line and the graph cross each other?
Period.
In this case, 2 times per period. So what you have to do is just make sure when you look at it on the screen, don't just tell me this answer and this answer. Tell me this answer, and then tell me that it keeps repeating itself. Tell me this answer, and then tell me that it keeps repeating itself. Okay? So what you have to do for that is put the plus period times n. Okay? So I just told you guys that. If you can find one solution, then it means you have infinite solutions, because that solution will repeat forever. So suppose you use your calculator, you do second calc intersect, and you find one solution. To write down all solutions, take the one that you found, and then just put plus the period times n. Now, which one do you have to find right here? It doesn't really matter. Doesn't matter. Okay. It's kind of like if I said to you, I want you to stand on a square in this room, and I want you to paint one square to the left and to the right forever. Doesn't matter which square you start on. Basically, if you start on any square in this room and you tell me you're going to paint one square left and right forever, eventually you're going to paint every square. Whether you start here or whether you start here. You're still going to cover everything. So that's why B doesn't matter. You can start anywhere you want. Just make sure you tell me to cover everything left and right. Okay? That's the idea. Okay, so we'll do the last problem on the calculator, and then and that's it. So one thing you're going to need is the period. So remember, 2 pi over b or 1 pi over b. Depends on which trig function you're doing. Okay. All right. So let's do. I'll do one with you guys that's a 2 pi, and then I'll do one that's a 1 pi. We'll try one of each. The top one is 2 pi. Look at the cosecant. What number is in front of x? 1. So there's no change to the period here. Period is 2 pi. Now, that's not an answer to anything we need yet in the problem. It's going to be part of my final answer. Brandon, how would I type in cosecant? Yep, we got to do 1 over sine because we don't have a button for cosecant. So we got that in there. That's fine. Type in -1.6. And now, if I look at Oops. If I look at this, to me, this is confusing because you're looking at more than one cycle on the screen. Okay? Your job is just to find the answers in one cycle. It's confusing. There's like 6 answers on the screen there. I don't want to look at that. I just want to look at one cycle. So let's make it simple. Let's look at 0 to 2 pi. Because you guys just told me 2 pi was the cycle. Now, the reason this simplifies it is because you're looking at one cycle. I want you to tell me everywhere on the screen that those 2 graphs cross. Just 2 spots. Every other cycle, every other intersection you guys were seeing on the screen was just a repeat of these 2. So secant, calc, intersect. And if you can't find where you are, just press the arrow enough times, eventually you'll pop up on the screen. Hit enter 3 times. 3.82. And secant, calc, intersect. Once you're more than halfway to it, you should be good. 5.61. Now, at this point, all you've done is tell me 2 specific answers. I want to know all of them. How often are each of these answers going to repeat? Yeah.
Once every cycle.
And the cycle length here is
2 pi.
2 pi. So make sure you put your answer plus 2 pi n. So if I wanted to know what's the next one after 3.82, I could just add 2 pi to it, and that would tell me the next one. And you know, tangent's pretty much the same, except with tangent, you only get one answer per cycle because it looks like this, and the line only hits once. So, any questions on how we did that? All right. So that's the homework for tonight, page 352. We'll take a look at that tomorrow. And like I said, I think this section's probably the hardest one for the week. Tomorrow and Wednesday, definitely easier. Maybe Thursday a little harder, but I'll be here after school on Thursday too if you guys need any extra help before our last test for the term.
So if it was like cosecant 3x, what would the period be?
Period would be 2 pi over 3.
Okay.
So your answers, without doing the rest of the problem, would each have this on the end of it. Plus 2 pi over 3n.
Okay.
This right here, use your graphing calculator to figure it out.